In this module, we're going to learn about a rule-based model, namely the Cubist model. The Cubist model is one of the current state-of-the-art algorithms that are deployed in machine learning for learning the association or the relationship between predictor variables and the target feature. But before we begin, let's take a step back and recall a very important lesson we learned in the last class about using regression trees for classification models. It will be very instructive for us to recall that regression trees are built in such a way that with recursive partitioning, we're able to generate a set of rules by which we can learn the relationship between the target feature and the predictor features. In order to enable that recall, let us consider a scenario that we discussed in the last class. The scenario we want to consider pertains to the Google App Store. We talked about how you have just started your first job at a Google App Store, and one of your main tasks is to be able to make recommendations of what apps your customers might potentially want to explore and download. Now, in the customer database, what you have as your training data is data on 6 past customers to the store. And here is the data. The first row is a profile that you have on a female 15-year-old customer to the App Store who eventually downloaded the Pokemon app. The second row pertains to the profile of a 25-year-old female who eventually downloaded the WhatsApp app. And the third customer is a 32-year-old male who eventually downloaded the Snapchat app. So, our target variable here is the app variable or feature. It's a categorical feature, which means this is a classification problem. And we would like to see if the information or the values we have in gender and age for each customer can provide information as to what app this customer might eventually download. So, the big question before us is, between gender and age, which one of these variables provides the most useful information in predicting what app a particular customer might eventually download? Was it gender? Was it age? Do you recall what we discussed then? Let's quickly review it. We recall that we said that if we were to make recommendations based on gender, then you observe that most females prefer WhatsApp more than Pokemon, whereas for males, most males preferred Pokemon than Snapchat. Well, that is for gender. What about for age? What did we recall? We said if we were to make a split of age where we talk about customers who are under 20, that is 15, 12, and 14, all of them downloaded Pokemon. That was very decisive, you may say. Whereas for those who are above 20 years old or who are older than 20 years old, they preferred WhatsApp to Snapchat. So it appears that in using age, which we discussed in the last class, we were able to have a more decisive route to go. Those who are under 20 simply recommend Pokemon to them, and for those who are above 20, we can either recommend either either WhatsApp or Pokemon. So with that said, we can summarize the insights in this data by using this decision tree. If a customer is younger than 20 years old, we'll simply recommend Pokemon Go. If the customer is older than 20 years old, then we need more information, and gender can provide that further information to give us the split. If the customer is older than 20 years old and also female, we'll recommend WhatsApp. Otherwise, we'll recommend Snapchat. So based on this decision tree, which summarizes the insights in this data set, we can say that if a 34-year-old female lady comes into the App Store at a future date, the app we would recommend is WhatsApp. So that was that about a decision tree for a classification problem. In this module, we will build on what we learned in the last class by developing a Cubist model in order to improve on some of the drawbacks that are associated with regression trees. Take note that the Cubist model is itself built on the heuristics of a regression tree. So without any further ado, let us get to the task. In order to motivate what we're about to discuss, we will consider an applied business use case. So here we go. In order for a health insurance company to make money, usually they need to collect more in yearly premiums than they will spend for beneficiaries of their insurance plan. And in order to ensure that they have enough money to cater to the health demands or the health costs of those who benefit from their health plan, insurers usually invest a great deal of time and money in order to develop models that can accurately help them to predict medical expenses for the insured population. So, one thing that has been found in the health insurance industry is that the costliest conditions can be rare and seemingly random. And some conditions can be more prevalent in certain segments of the population. That is, for example, certain age groups tend to have more instances or more incidences of some type of diseases or not. Now, the goal of this analysis is to use patient data to predict the average medical care expenses for such population segments. How can this be of any value? Well, the estimates that we generate in using a predictive model can be used to create actuarial tables that can be used as a price setting benchmark of yearly premiums, so that they are either higher or lower according to expected treatment cost of the different patients. So at this point, we would like to look at what the data set we have on this patients contains. So the data we have includes 1,338 examples or profiles or information pertaining to 1,338 patients who are currently beneficiaries of the company's insurance plan. And the target feature that we would like to predict is the medical expense of the patient. The predictor features that we would like to collect information from in predicting the medical expense of a particular patient are age, sex, BMI, number of children, whether the person is a smoker or not, and the region of the United States where the person is residing. So, as usual, the first step we would like to take is to explore the data. So, I have used R as usual in order to provide a summary of the features that we have in this data set. As you can see on the screen, we have 3 factor or categorical variables and 4 numerical variables. For the categorical variables, we have sex, smoker, and region. We do not have any missing rows. The complete rate is 100%. None of these factored variables are ordinal, and you observe that we have just roughly about the same number of males as we have females, but we have more non-smokers than smokers, and there's roughly an equal distribution of these patients in the different four regions that are being considered. And then we have age, the BMI, the number of children, and the expenses. And we have the summary statistics of each of these numerical variables. So we would like to recall that our target feature is expenses here. And in this tiny histogram here, we can see that this is a right-skewed distribution. And the reality here is that since we are trying to build a regression tree, we would not need to do as much pre-processing. And to remind us of what we discussed in the last class about regression trees, you might want to recall this statement by Max Kuhn and Johnson, in which we learned some of the appealing characteristics of deploying regression trees for understanding the currents of relationships between the target feature and the predictor features. The first thing is that they generate a set of conditions that are highly interpretable and are easy to implement. They can also handle different types of predictors, whether sparse, skewed, continuous, categorical, without the need to pre-process them. And that is something that is very appealing. Then in addition, these models do not require us to specify the form of the predictor's relationship to the response, much like we do in linear regression, where we make assumptions, in order to understand, where we make assumptions about the relationship between the response variable and the predictor variables. Then, we also mentioned in that class, or in the previous class, two well-known weaknesses about regression trees, namely model instability. A little bit of change in the training data can sometimes drastically change the structure of the trees or rules, and that would also mean that the interpretation of the model itself would also change. Then sometimes you can also have less than optimal predictive performance. And that is one of the key motivating reasons why we are considering this improvement on single regression trees in the form of Cubist models. So for this data set, we would like to take a step back and first build a regression tree model. So to do that, here we are in R. We load the RPath library, and we use the formula method in order to specify that expenses is the target feature, and would like to consider how expenses depends on all other columns in the training data set. So here is a visual, in which case we can see that the variable or the predictor variable smoker appears to be the single most important variable in predicting the expenses, the medical expense of a particular patient. There are other variables or features that this model has been able to successfully select as important in providing information about predicting the expenses of the medicals of patients in this data set. And that includes the age of the patient, the BMI of the patient. You might want to recall that when you look at your single regression tree, this is the root node. 1, 2, and 3 are the interior nodes, and all of the leaves, all of the nodes right at the bottom are all leaves. And that was specified in this argument of the arrow path dot plot, where you have falling leaves set to true. As far as the interpretation of this regression tree goes, one quick path we might follow to illustrate, based on what we discussed in the last class, is that out of the 935 observations in the training data set, if a person is found not to be a smoker and is aged less than 45 years old, there are 431 of them, and they constitute 46.1% approximately of the total 935 training instances, and the predicted amount, or the predicted medical prices for everyone in this node that satisfy this rule is $5,559.09 approximately. Well, it's no surprise that they seem to cost less in medical expenses than smokers, that is, those who are smoker equals yes, and whose BMIs are greater than 30.1, and we have the age greater than 42, and in which case you have a higher medical expense or predicted medical expense. This is the appropriate time to remember that, as appealing as this model is, very highly interpretable, very relatable, the major disadvantage that we talked about earlier is that they are highly unstable. And that means that if you change the training data set, there might be variations in the variables that will be chosen as the most significant variable in predicting medical expenses. Now, that is not as much a desirable quality of a predictive model. So that takes us to looking for other models that might better exhibit increased stability and still be able to capture the pattern of the relationship between the target feature and the predictor features. But before we do that, let us evaluate this model on the training or on the test of validation instances. Here is the actual medical expense. Here are the predicted medical expenses. So actual minus predicted, you have the error of predictions. For some, the model was close, and for some, it was not performing as well. And the performance metrics of this model, in which case you have the RMSE. The RMSE for the single regression 3 was at $5,376.9, and the mean absolute error was at $3,505.82 with R square of approximately 80.86%. Now, at this point, we want to review the no free lunch theorem, where we know that no model is universally true or best fit for all kinds of data. So that leads us in the search for a better model for this data set. And that brings us to the Cubist model. The Cubist model is an improvement or an enhancement of the single regression tree, where rather than using the average medical expenses of every patient in a particular leave node to predict what is the medical expense of every such patient in that node, we replace that average by building a regression model based on every instance in the leave at that point in time. So with that said, we can build a Cubist model by using this syntax. And with that, we have the following Cubist model. And the first rule we have here talks about the age